Welcome back to Introduction to Software Reverse Engineering. In this module, we will review the basic arrays and focus on practical aspects of working with them in Ghidra. Get ready for a lot of practical work today. Welcome to Module 10. In this module, we will build on top of Module 5 that covered some basics of arrays. Today we will recall that knowledge and focus on practical matters of working with arrays, both globally available in the program as well as arrays local to a function. Let's start. There are a few goals I want to achieve in this module. First, revisit Module 5 and its coverage of arrays of basic types. Second, familiarize you with identification of code patterns that are relevant to arrays, both global arrays as well as arrays local to a function. Third, I want to build your skill identifying size of array elements. This is very important and builds up to the next module in this course. And lastly, to look at an interesting example of an array data visualization in Ghidra closer to the end of the module. All the materials covered in this course are available on GitHub. The link is on the screen right now and also available in this description to the video. First, start Ghidra and import arrays.exe example program. In this module, we will reverse engineer functions from this binary. Once the program is imported, double-click on it in the list of imported binaries and perform automatic analysis when prompted in Code Browser window. While the program is being analyzed, let's take a look at the source code of the first function that we are going to reverse engineer. Here it is. The function allocates an array of integers on the stack and prints the values from the uninitialized array using printf function. Let's take a look at the decompiled version of the function and inspect its body. First, there is a variable with the number of iterations for the loop on line 7. Second, then there is a loop. And third, there are two calls of printf function. The printf function calls do not have all the parameters, which is expected and discussed in detail in Module 8 that covers variadic functions. Now, let's make sure that these are indeed printf functions. Double-click on the parameter of the function on line 9. The parameter is indeed a format string, a short format string. The second call of printf function on line 12. Although it is not obvious, it is a short format string as well. It has just one character. Double-click on the function either on line 9 or 12 to verify that this is indeed a printf function. The function's body is shown on the screen. It does look like printf function, given the first parameter is the format string, and it has the attributes of variadic function. See automatic stack variable use on line 9. Modify the function signature so that it reflects the function's variadic nature, and rename the function to printf, as shown on the screen. Now, let's navigate back to the function we were reverse engineering a minute ago. Once the printf function obtained its proper signature, Ghidra was able to pull in additional previously hidden variables into the decompile window. Local 3c variable is now present on the screen, and unsurprisingly, it is detected as array of 15 elements, same as the number of iterations set on line 10 of the function. Given that the array was not initialized, Ghidra had hard times identifying it, especially when the printf function signature was out of order. Before moving on to the next example, note that the listing window shows sub-ESP assembly instruction with a value of 3c. This relatively large value for such simple function should prompt your curiosity regarding why so much space was allocated on the stack. Now, let's explore another example. The next example function is a bit more interesting. It allocates two arrays in the scope of the function and populates them with the help of two different functions. Then it prints the second array, a variable named message, with the help of printf function. Let's take a look at its decompiled version. It's quite verbose. Let's break the function down into the parts. First, we know that getSystemDirectoryA function accepts a buffer and the length of the buffer to ensure that there is no memory corruption. However, local 23c variable was identified by Ghidra as one character, instead of an array of 260 characters. To fix this, right-click on the variable and select Retype Variable in the context menu as shown on the screen. The Data Type Chooser window will appear on the screen and display current assigned type of a single character. Change the data type to an array of 260 characters as shown on the screen. In most cases, Ghidra supports decimal and hexadecimal input for numbers throughout its various screens and windows. Click OK to apply the change. With the new data type applied, the function's body has changed. The variable declarations are updated at the top of the function, and the initialization loop changed to reflect nature of 1 byte long character data type. Note that lines 12 through 20 initialize the first array with zeros. The same array initialization with zeros in the source code looked like a simple operation expressed by just a few characters. Now, let's take a look at the function on line 28 and its second argument. The value of the argument looks like a format string. Let's take a look at the function itself. This function is the printf function. It can format a string based on the template, and instead of printing the result in the console, it populates the first parameter, the buffer, with the result, the formatted string. Note that the function has the automatic stack variable, however, its name ends with C instead of 8, as we have seen with the printf function earlier. Change the name of the function and its signature so that it matches the signature shown on the screen. Now, let's return to the previous function. Now, after all this analysis, the function's body, although still very verbose, makes a lot of sense. This printf function has all of its arguments in place. Now, I would like to talk about the size of the variable ACStack138. Ghidra shows that it is 312 bytes long, and the math of stack subtraction for the local variables adds up to 312. However, let's verify that with the original source code again. The original source code has the second array length set to 310 instead of 312, identified during the reverse engineering analysis. Those 2 extra bytes are there because of the need for the stack to be aligned with the platform word, which on 32-bit system is 32 bits, or 4 bytes. The 310 bytes do not meet this requirement, but 312 bytes do. Now, let's inspect another example function. This function contains multiple loops, reading and writing to global arrays that are defined just above the function. And finally, it prints these populated values to the console. The decompiled version of the function is shown on the screen. Observe that the nested loops were transformed, so that the inner loop still has the maximum iteration count defined as 17, see line 16. However, the outer loop exit condition is transformed to be compared not to a maximum iterator value, but to a pointer in the memory. For such exit condition to work, the memory location that the pointer is pointing to must lay outside the boundaries of the array. The inner loop was preserved by the compiler so that it uses the iterator value as the exit condition. An important piece of information that always comes handy when dealing with arrays is to know how large each item of the array is. See that the array iteration pointer is being incremented on line 21 in the decompile window. However, the listing window shows the true value, 4 bytes. The reason for this is that the decompile window applies the pointer arithmetic rules as they are working in C and C++, where a pointer increment operation increments the pointer by the size of the array's element, whatever it is for the pointer in question. Now, let's take a look at the resulting array that the function populates. Double-click on it. Hit open bracket hotkey while the array is selected to bring up the Create Array window. Ghidra will suggest 1450 elements to it, as shown on the screen. This is definitely an overstatement. Click Cancel to close the window. Scroll the listing window down until you see the next cross-reference user interface element, which is not the second element of the array. You will find the next cross-reference user interface element as shown on the screen. Unsurprisingly, its address matches the exit condition for the loop that iterates over this array. See line 30 in the decompile window. Now, let's calculate the size of the array. To do so, subtract the starting address from the address of the cross-reference after the array. The result of such subtraction is 330 in hexadecimal, or 800x16. Also, the result is in bytes, not the number of the elements. To get the number of elements, divide the total size by the size of each element, which is CC, or 204 elements. Go back to the beginning of the array and retype the variable to an array of 204 4-byte long elements. Click OK to apply the change. Ghidra will apply the change and decompile the function once more. Note that the global variable name changed to null array. This is the case when an array is an array of undefined data types, instead of known data types such as int or float. Let's perform the same process with the second array. We know the array starting address and the address right after it, as shown on line 12 and 24 in the compile window. Double-click on the end address to see the program's memory at that location. Now, subtract the array address from the array's end address as shown on the screen. The result is the length of the array in bytes, which is 30 in hexadecimal or 48. Retype the variable to an array. Ghidra will suggest 14 elements, which we know is untrue. Type in 12 and click OK to apply the change. Both the listing and the compile windows will update to reflect the change. Note that this array has values embedded into the array. The previous array was full of zeros. This one has initial values. Now let's also look at the format string of printf function. The format string is useful when it is available because it provides strong signals toward what data types we're dealing with. In this case, this is an integer as indicated by the D template value. Change the format string data type to a string. This covers the analysis and reverse engineering of this function and two global variables that the function uses. Now, let's take a look at one more example function. The last example in this module is another simple function that iterates over a short array of 5 bytes. Let's take a look at its decompiled version. The decompiled function is striking, especially line 8, which is rather unique. Note that the pointer to the array works as expected, incrementing the pointer by 1 byte at a time. What explains this unique representation is that Ghidra decided to visualize the array as a string, instead of a global array as we have seen in the previous examples. This is it for this practical module on arrays. Thank you for learning with me today. In the next module, we will take a leap from working with basic data types to working with complex data types, structures. We will examine the tools Ghidra has to offer to deal with structures, and explore some new example programs that showcase structures in action. All the materials for this course are available on GitHub via the link shown on the screen and in the video description. These materials include the source code as well as the compiled binaries themselves. See you in the next video. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.